Hi, I'm An, and welcome to the first video in this series where I plan on covering the entire WA Year 12 Maths Applications course. Now, this course is known as General Maths in most other states, except for New South Wales, who call it Maths Standard Stage 6. There is a bit of variation in the course between the different states, so if you are watching this from outside of WA, please bear that in mind. Now, as you can see here, the first topic that I'm starting with is graph theory. This is not the first topic in the syllabus, but it introduces so much new terminology that I think it's worth learning earlier rather than later. Okay, so the first term that I'm going to talk about is graph or network. This is simply a diagram that has a set of points and some connecting lines. A single point on our graph is called a vertex or a node, and if we're referring to them collectively, then we'll use the plural, which is vertices or nodes. We often label our vertices with letters and usually in some kind of alphabetical order because we like to be systematic in maths. The lines connecting the vertices are called edges, and in my example on the screen here, every single edge is undirected. This means that there's no restriction on the direction that I can travel along this edge. So I can start at A and travel along this edge to B. I can also start at B and travel along this edge to A. However, if I add an arrow, this now becomes a directed edge, also known as an arc, and it acts like a one-way street. So I can start at vertex B and travel along this edge to vertex A. However, there is now a restriction that tells me that if I start at A, I can't travel along this edge back to B. Okay, next we have faces or regions of a graph. And these are just areas that are bounded by edges. So on my graph here, you can see this area in green, that is one face. I have another face here in yellow. And then something that we need to keep in mind is that we need to include the outside face, so this area here in pink, as another face. So in my graph here, I have 1, 2, 3, 4 vertices, 1, 2, 3, 4, 5 edges, and 1, 2, 3 faces. Now we say that two vertices are adjacent if they are directly connected by an edge. So in my graph here, A and C are adjacent vertices because they're directly connected by this edge here. Another pair of adjacent vertices is A and B because, again, they are directly connected by an edge. They're actually connected by two edges. Now, B and C are not adjacent vertices because there's no edge directly linking them. However, we can say that they are connected, and in this case, they're actually connected via vertex A. Sometimes we encounter an isolated vertex, which is just a vertex that isn't connected, or in other words, it's all by itself. So in this example here, D is an isolated vertex. And because this graph has an isolated vertex, we can say that this graph is disconnected or unconnected. Now, a loop is just an edge that connects a vertex to itself. So in my example here, there is a loop at vertex C. Next in our graph here, we can see that vertex A and B share more than a single edge between them. There are actually 3 edges. So we say that this graph has multiple edges, or more specifically, vertex A and B share multiple edges or parallel edges. Now, a bridge is any edge that, once removed, makes the graph unconnected or disconnected. So in my graph here, there are 2 bridges. The first bridge is AC because if I remove that edge, the graph becomes disconnected. And the second bridge is CD because again, if I remove that, it becomes disconnected. Now, the degree of a vertex is the total number of edges that are entering or exiting that vertex. So what I like to do is just to circle the vertex and then count up the number of edges. So vertex A here has a degree of 1. Next, for vertex B, there are 1, 2, 3 edges, and so it has a degree of 3. And vertex C here has a loop, and you can tell once you circle the vertex that a loop actually counts as 2 edges when we're considering the degree. So 1, 2, 3, 4. Vertex C has a degree of 4. Now, when we're talking about the parity of a vertex, that's simply whether it's odd or even. So vertex A is odd because 1 is an odd number. Vertex B is also odd, and vertex C is even. Next, we have a directed graph, or a digraph for short, which is just a graph that has directed edges or arcs. And as you can see here, I've got 2 arcs, AC and CD. So this is an example of a digraph. Next, we have weighted graphs, which are just graphs that have weighted edges. When I'm talking about a weighted edge, that's just a value that is assigned to the edge, and this has lots of practical uses. Sometimes that might represent the distance between 2 towns, or maybe the running costs. Next, we have complete graphs. Now, a complete graph is one where each vertex is connected to every other vertex. We use capital K with a subscript value of n for the number of vertices when we're referring to a complete graph. So K3 is referring to a complete graph with 3 vertices. K5 is referring to a complete graph with 5 vertices, and so on. A formula that you'll find useful for complete graphs is this one here, n times n take 1 over 2. This gives us the total number of edges of any complete graph. So let's fact check this and consider the graph K4, which is a complete graph with 4 vertices. N equals 4 is what we're going to substitute into this formula. So 4 times 4 take 1 all over 2 is equal to 4 times 3 all over 2. 4 times 3 is 12 divided by 2 is 6. So we're saying that K4 has 6 edges, and when we check on our diagram here, we've got 1, 2, 3, 4, 5, 6 edges. Feel free to fact check this for any complete graph. Next, we have a simple graph, which is simply a graph that has no loops, no multiple edges, is undirected, and is also unweighted. So here's an example of a simple graph. Notice that it doesn't have multiple edges nor any loops. Now, I do want to point out that ACBA is a cycle or a circuit. It is not a loop. Remember, loops only connect one vertex to itself. Next, we have a walk, which is a connected series of vertices and edges that exist in a graph. So in this example here, I can start at C, travel to D, then to B, A, C, maybe back to A, and back to B. So that is an example of a walk. Next, I have a trail. Now, a trail is still a walk, but there's a special condition that you can't repeat any edges that you've already traveled along, but you can repeat vertices. So as an example, on my graph here, if I start at vertex A and travel to B, then to C, and then back to B, but along a different edge, and then to D, and then to C, I have repeated the vertex B. However, I haven't repeated any edges, so that is a trail. Next, we have a path, which again, actually is still a walk and it's still a trail, But there's now two conditions. We can't repeat any edges and we can't repeat any vertices. So an example of a path on my graph here is starting at E, traveling to C, then to D, then to B, then to A. I haven't repeated any edges or vertices, and so this is a path. Now, walks, trails, and paths, these all have subclassifications because each of these can be open or closed. What I'm going to look at first here is an open trail. So we know the rules of a trail. We can't repeat any edges, but we can repeat vertices. And if it's open, that means that it's going to begin and end at different vertices. So let's look at an example. If I start at vertex D and then travel to C, then to B, and then back to C again, and then to E, this is an open trail because I didn't repeat any edges, but I did repeat vertices and it begins and ends at different vertices. Next, we have a closed trail, also known as a circuit, and this is simply a trail that begins and ends at the same vertex. So, as an example on my graph here, starting at vertex D and then traveling to C, B, back to C again, and then to E, and then finally finishing at D, which is where I started, to create a closed trail or a circuit. When you're trying to decide whether edges or vertices have been repeated or not, this doesn't include the beginning and the end vertex. So D is not repeated, however, C is a repeated vertex in this circuit. Next, we have an open path. So this is just a path that begins and ends at different vertices. As an example, if I start at B and then travel to C and then to E and then to D, because I didn't repeat any edges or vertices, this is an open path. Next, I have a closed path, also known as a cycle. So this is a path that begins and ends at the same vertex. On my graph here, if I start at B and then travel to C and then to E, then to D, and then one last edge back to B here, because this is a path that begins and ends at the same vertex, it's called a cycle. I didn't repeat any edges. I also didn't repeat any vertices. Okay, remember the beginning and end vertex is not counted as a repeated vertex. Now, because this can get quite confusing, I have created a little flowchart here that will help you answer whether it's a walk, a trail, a path, a circuit, or a cycle, and this is available to download via my website in the description box below. Now, when we refer to the length of a walk, we're also referring to the length of any trail, path, circuit, cycle. The length of a walk is the total number of edges that walk has. So in this graph, if I start at vertex C and then travel to A, 1, to B, 2, D, 3, back to A, 4, back to C, 5, and then finish at D, 6. Because that walk has 6 edges, the length is 6. If you're writing down the walk like this, count the number of vertices, 1, 2, 3, 4, 5, 6, 7, and then don't forget to take 1 because remember the edges only exist between each pair of vertices. So 1, 2, 3, 4, 5, 6 edges there in between each pair of vertices. And finally, we have arrived at the last term for this lesson. It is a subgraph. Now, a subgraph is a graph that forms part or whole of another graph, and it also doesn't introduce any new vertices or edges. So let's look at this graph here. We're going to call this the original graph. If I remove a vertex and a few edges and I don't introduce any new vertices or edges, This is now a subgraph of the original graph. Now, if I remove another vertex and another couple of edges, I now have a subgraph of a subgraph. It does get a little bit inception-y. Now, this graph here, graph 2, is now a subgraph of graph 1, but also of the original graph. And the last thing to note is that every graph is a subgraph of itself. Okay, we're going to look at some examples now. In this first question, we're just identifying key features of this network here. The question says, consider the graph to the right, state the number of vertices. Well, let's just count them up. 1, 2, 3, 4, 5. So this graph has 5 vertices. State the number of edges. Again, we'll just count them up. So 1, 2, 3, 4, 5, 6, 7, 8 edges. So this graph has 5 vertices, 8 edges. Now part C says, does the graph have a bridge? Explain. Remember, the definition of a bridge is any edge that once removed makes the graph disconnected. So in this graph here, I can see that CD is a bridge because if I remove that, the graph becomes disconnected. And that's what I'm going to write. CD is a bridge because if it's removed, the graph becomes disconnected. Moving on to part D. So, state the degree and order of vertex C. So remember, when I'm finding the degree of a vertex, I'm going to circle it and then count up the number of edges. So vertex C has 1, 2, 3 edges. Therefore, it has a degree of 3, and that's odd. Vertex E has a degree of 1, 2, 3, 4, and that's even. Part E, what is the minimum number of edges that need to be removed so that it is a simple graph? So we need to know the definition of a simple graph. Undirected, unweighted, check, check. However, it also needs to have no multiple edges and no loops, which our graph is violating both of those rules at the moment. A and B share multiple edges and D and E share multiple edges. So I can remove one of these edges and one of these edges, and I also need to remove this loop. So in total, the minimum number of edges that need to be removed is 3. 3 edges. All right. Next, what is the length of the longest trail? So trail, remember, means that we cannot repeat any edges, but we can repeat vertices. And it doesn't matter whether it's open or closed in this case. So I might start at the loop at vertex E. So I've got 1, 2, 3, 4, 5, 6. I think 6 might be the longest, but I'll try a couple of other things. 1, 2, 3, 4, 5, 6, 7. Actually, the longest trail is 7. Did you see that? Can I do that again? Maybe I'll start at vertex C. 1, 2, 3, 4, 5, 6, 7. So notice that I didn't repeat any edges, but I did repeat a vertex, especially at that vertex E there. So the length of the longest trail is 7. And part G here is asking me to state a cycle that has a length of 3. So a cycle is a closed path, meaning that we can't repeat any edges. we can't repeat any vertices, and it needs to begin and end at the same vertex. So a cycle that has a length 3, well, there is one possible cycle over here of length 2, for example, E, D, E, but I'm going to use this one over here. I'm going to start at A, travel to B, to C, and then back to A. So 1, 2, 3, that's a length of 3. And I'm just going to state the cycle. I'm going to start at A, B, C, and then back to A. Okay, example 2 here is all about constructing a graph given particular circumstances. So the question is asking us to construct a connected graph that has 4 vertices, 5 edges, and all even vertices. All right, few key words here: connected, 4 vertices, 5 edges, all even vertices. I'm going to start by spacing these 4 vertices nice and evenly apart. Okay, so I've got 1, 2, 3, 4 vertices there. And now I'm going to try and fit 5 edges in. And as I'm doing this, I'm going to maintain even vertices. So when I add an edge between these 2 vertices, the degree of this vertex is currently 1, which is odd. So I'm going to add another vertex so that that degree is now 2. And my vertex at the bottom here also has a degree of 1. So I'm going to add a line maybe this way. Currently, all 3 of my vertices have even degrees, but it's not connected yet. I'm going to add another edge here. 1, 2, 3, 4. Okay, I've got 4 edges. I only have 1 edge left, and currently the degrees of my vertices are 2, 2, 3, and 1. So to make 3 and 1 even, I'm going to add an edge that connects them. And so now this vertex has a degree of 4, this vertex has a degree of 2, and that satisfies our conditions. 4 vertices, 5 edges, and all even vertices. Now, the only other possible option of creating 4 even vertices with 5 edges is if you were to add a loop. So let me maybe add 4 edges first of all. Currently, I have all even vertices. So if I add an edge on, I'm going to end up with 2 odd vertices, and I don't want that. So I can add a loop. That's my 5th edge. And now this vertex has a degree of 4, while the others have 2. The third and last example today is looking at simple graphs and complete graphs. So consider the graph below, considered. How many edges need to be added to make this a complete graph? So this graph has 1, 2, 3, 4, 5 vertices, which means if I'm trying to turn it into a complete graph, I'm going to try and get K5. I can find out the number of edges for K5, which is going to be 5 times 5 take 1 all over 2, which is 5 times 4 divided by 2, that is 10. So a complete graph with 5 vertices is going to need 10 edges altogether. So let's count up how many we currently have. 1, 2, 3, 4, 5, 6, meaning that 4 edges need to be added to make this a complete graph. And last but not least, how many edges does K8 have? So again, we can just use our formula where n is equal to 8 because there's 8 vertices. 8 times 8 take 1 all over 2 is the same as 8 times 7. divided by 2. Half of 56 is 28. So K8 will have 28 edges. And that brings us to the end of this lesson. Thank you for joining me, especially if you're still here all the way at the end. I know I covered a lot in this lesson. In the next one, I will be looking at some practical applications of matrices, so weighted graphs and digraphs, but also adjacency matrices and also bipartite graphs. All right, I'll see you then. Bye.